Okay, so first thing that we're gonna do before we actually do the notes today is look at different derivatives of composite functions. So this is pretty much, let's make a prediction and then we'll take the notes after we figure out what the relationship is. This just seems easier than having you guys take notes with all of this stuff.
If you want the
All right, so the first thing that I want to do before we actually look at the derivatives is look at what the composite functions actually are. I'd like to know what the inside function is and the outside function is. That way we can recognize that these are actually all composite functions. So looking at number 1, can anyone tell me what that inside function is in either of the versions?
3x.
Yeah, 3x plus 5. Outside function? Yeah, that entire thing raised to the 1/2. So we'll say parentheses to the 1/2. And you could treat the parentheses like, hey, this is my variable. I want you to go ahead and do that with all 3 of these functions. In Zoom, I expect that you're following along on the paper. All right, let's take a look at function 2. Anyone want to tell me the inside and the outside? So inside sub next minus 5. What's the outside? Cubed. So parentheses to the 3rd power. My suggestion when you guys are doing this in the notes, whenever you're at the parentheses, I didn't quite do that here, but write the parentheses as long as that inside function is. So maybe I would widen this up a little bit. That way later on I can put the inside function back in there. And then what is the inside and the outside for the 3rd function? Anybody? So what's the inside?
5x minus 3.
Just 5x minus 3. Okay. And the outside? Yep. Just that expression to the -1. So parentheses to the -1 power. Look all right so far? Now, if you don't like using the parentheses, you can use a different variable to substitute it, one that isn't used anywhere. Like if you want to use a cute I, if you'd rather say inside to the -1, you can do that as long as later on you know, okay, I'm going to put the inside function back where the I is. Or instead of the parentheses, you're going to put that inside function back where the parentheses are later. All right, and then I gave you guys a special one that I'm just going to add to the board. Anyone want to take a guess as to what that inside function is? So you're plugging E into the outside? So what would E get plugged into? You disagree, Alex? What do you think?
inside is E to the F. No, that's the inside is 7x squared minus 3x minus 6.
Let's see if that works. And what are you saying the outside is?
E to the X.
Or e to the parentheses?
Yeah.
So if this is my outside function and I go ahead and plug the inside into it, would I get the same thing? Yeah. So it's all about, I mean, this is why I put this one up on the board, because I have seen a few people struggle with that one. Just think about what's getting plugged in here. E is actually an exponential function. You plug things into exponential functions. So E would happen to be the outside where you're plugging that polynomial into it. Okay. Oh, and one more thing. You guys notice how wide my parentheses are? Again, that way I can fit the inside function in there later. So do we have any questions about identifying inside and outside? No? Okay. What I would like you guys to do now is the prediction. This is going to take you guys a few minutes maybe. I want you to look at each of the composite functions, like the original function itself, and compare it to the final simplified derivative. I want you to write down any patterns you see if you can come up with a general rule. Maybe even if you guys use the word outside and inside, since I use that everywhere up there, that might be helpful too. Tell me what you notice. And up on this marker board over here, which I'll add to the screen, I have each of the final derivatives simplified a little bit further or broken up a little bit further. That might help you be able to make your prediction or see that potential rule. All right, so what did we notice? Any group want to share? Carly?
The coefficient on the outside is like the outside power times the derivative of the inside.
Let me write this up. So you said what?
So like the coefficient on the outside is basically the outside power times the derivative of the inside.
Then
And then the same inside to the outside power minus 1.
so basically use power rule on that outside function. And then you multiply by the derivative of the inside, which all of our inside functions happen to be linear, right? So they were all coefficients. So if you said you multiply by the leading coefficient, that's okay. Because that's what you notice here in all of these. One thing that I want to make it a little bit more general, instead of saying power rule for that outside function, what is power rule used to find? The derivative. So you essentially took the derivative of the outside, which is all this, right? So that's power rule, everything that I have underlined. So that's essentially the derivative of the outside. Times the derivative of the inside. Let's check and make sure that works for all of these. Pretend the parentheses are just blank. Does that look like the derivative of the outside for number 3? Multiply by the power, subtract it by 1. Does this look like the derivative of the inside? Yay, nay. Derivative of 5x minus 3 is 5, right? function 2, parentheses to the 3. Does that look like the derivative of the outside? Derivative of the inside? Front. What would the derivative of this outside be while I have this up here? Let's see, do we have that down here? Yeah, we have that. And then the derivative of the inside, would that have been 3? Perfect. Now, like I said before, if the insides happen to be anything other than linear, saying derivative of the outside is derivative of the inside makes that a little bit more general. If you were a leading coefficient on this, that's all right. Because here we have our notes. We're gonna write the general stuff up. So there's a reason why I've been avoiding taking the derivative with. Oh, I think I do. Taking the derivative with multiple things on the inside of a root. Or taking the derivative of e with anything other than just a single coefficient up there. So we're going to write this up formally. If I have a composition of functions, f of g of x, first of all, can you guys tell me the inside function? G of x, and the outside would be f of x. And they're both differentiable, and I want to take the derivative of that composition. Start off with the derivative of the outside, which you guys just said the outside was f. So we'll take the derivative of f with g of x inside. Then multiply by the derivative of the inside, which is g of x. So just label that, there's plenty of room. Derivative of the outside. Times the derivative of the inside. We're also going to write this up using Leibniz notation. So when I look at the derivative of the outside, I am taking the derivative of f, right? That outside function is f. But I'm not going to be taking the derivative with respect to x there. What's getting plugged into f? So we'll take the derivative with respect to g. When you're just taking the derivative of that outside function, you remember how we left the parentheses alone and then we had the inside put in there later? You treated that entire inside function like it was a single variable. So you don't do anything with that yet. Then how would I write up the derivative of the inside? Yep, dg dx, derivative of the function g, and then it'll actually be with respect to x. So every time you write up that little differential, derivative of that outside function, and then the inside function is what you're taking it with respect to. And we could do multiple compositions. You could go 2 compositions like we have here, inside, outside. You could have 3 compositions, inside, inner, outside. Yeah, working your way inside out. You could have 4 compositions, 5, 6, 7, 100. I'm probably just going to stop at 4. 5 would probably be a bonus problem. Yeah, I'm not going to make us do too many. So I have 2 examples here. We're going to do them heavily together, especially while we're learning. I would like you guys to go off to the side and label the inside and the outside, which we should be prepared to do now that we've done an example like this together. All right, what's our outside function? Try again.
The parentheses.
Yeah, e to the parentheses. E is the outside function that you are plugging what into?
X squared minus 4x.
X squared minus 4x. Now, just so I'm prepared for this later, what is the derivative of the outside? Yeah, just e. Derivative of the inside?
2x minus 4.
All right, I would like to give you guys a second to go ahead and write up what you think the derivative is. Anyone want to give it a go? Carly?
It would be 2EX. Us multiplying 2x minus 4.
What did you have written first?
E to the power of x squared minus 4x times 2x minus 4.
Almost, I like that. There's one technicality that you're missing.
Is it e to the x times 2x minus 4?
Jackson. Parentheses, specifically around the 2x minus 4. Because it's that entire derivative of the outside getting multiplied by the entire derivative of the inside. So yeah, we have the derivative of the outside here, which is just itself. Is its own derivative times the derivative of the inside. Notice over here, instead of the parentheses, we actually wrote the inside function, x squared minus 4x. So you'll go ahead and put that back in. We're just kind of using the parentheses as a placeholder in the meantime. Now you can leave the derivative like that. There's really not too much simplifying that you can do from here. I honestly think that's as simplified as I'd be willing to write it myself. Any questions? Okay. Example 2. Can anyone tell me what they think the chain rule is going to be like? What's the inside, what's the outside? It looks a little weird.
Inside is x cubed.
Inside is definitely x cubed. Mason?
It's outside c times.
Yes and no. So those are both outside functions, but not necessarily together. So do you guys notice how we technically have a product going on here? So we're going to be using chain rule when we take those individual derivatives. Like when I want to take the derivative of that first one, I'll use chain rule on that. Derivative of outside times derivative of inside. So yes, there are technically 2 outsides.
Product will multiply them together.
Yes. I'm gonna use it at the same time, but let's organize our stuff up over here. So first function, what's the derivative of secant? Anyone remember? Secant tangent. And anyone remember the derivative of sine? Derivative of the inside? Perfect. I would like to see what you guys come up with for the derivatives. If you don't want to write on your paper, you think that you're going to end up having to do a lot of erasing, I can get you a scrap piece of paper to write this on, or I can get you a marker if you'd rather do it on the table. I would like you to go ahead and try product rule with these composite functions. You don't need to simplify, just write up like what the first line of all of this would look like. All right, so let's go ahead and check your work. Okay, so we have a product here. I want to work on taking the derivative of secant x cubed first. So secant would be the outside, correct? What's the derivative of the outside of just secant? Secant tangent. All right, so that's the derivative of secant times the derivative of the inside, which we said was 3x squared. So we have the derivative of it first, then what?
Would be secant x cubed.
So we have the derivative of secant x cubed, then what do I do?
Log of times sine x cubed.
Yep, times that second factor. Okay. Plus. Yep, plain secant x cubed times the derivative of that sine x cubed. What's the derivative of sine x cubed?
3x squared cosine x
I'm gonna write it backwards and then I'll write it the forwards way later.
cosine x cubed times 3x squared.
Perfect. So cosine being the derivative of the outside sine. 3x squared being the derivative of the inside. We okay with all this? Now there's a bit of simplifying that we can do. Can anyone tell me anything that they're seeing? I don't want to do any like factoring yet, but if you see anything that we can simplify. Carly, you told me first earlier, so I'll let you go first.
Secant x cubed times cosine x cubed, would that be just one?
Yes, since secant and cosine are reciprocals, they would cancel and become one. Is that what you were going to point out, Alex?
Well, also, but secant theta times sine theta.
Yes. So we could have probably just rewrote the function at the very beginning. I wasn't going to let us do that because I wanted to practice using product and chain at the same time. But yeah, secant, let's just, use theta. Sine theta, that's really 1 over cosine times sine, which as Alex said would be tangent. So if I'm taking this and that and rewriting that as tangent, I'm going to have a tangent x cubed times tangent x cubed. So that would become a tangent squared. Plus that plain 3x squared at the end. Is everyone okay with that?
Probably. That's not right.
Around what?
Tan squared, 3x squared.
You don't necessarily need it because it's not like I'm distributing it to anything. Or I could just write that 3x squared first and not make it a non-issue.
But how did it go? From the first.
How did I get this?
Yeah, not a square.
Oh, the tangent squared. So secant times sine is actually tangent. Because that's 1 over cosine times sine. Or sine over cosine. Yes. No, that's good. One last thing that we can do to simplify. Do you guys notice that there's something in common in every single term? Yeah, there's a 3x squared. Factor that out, what are we left with? Perfect. Tangent squared x cubed plus 1. Do I need you to simplify that far?
I really don't think
No.
That's simple.
I mean, doesn't that look a lot better than the first line?
No, I mean, from line 3 to 4. I
It
just
depends on what you need. So like if I said to find
like if you-
the zeros for the derivative, you would end up factoring and then solving each factor, right? That would be a lot easier to do by hand than the previous line. But if you don't have any purpose, like if this is the very if I'm just asking for the derivative, honestly, you'd be fine stopping at that first line. Especially if it's on the AP test and you're not doing anything further with it. Stop there.
What if they say something?
Then you need to know how to simplify, which is why we practice it in class. And I kind of expect you guys to try to simplify on your practices. But if you answer the question, I'm not going to dock you points.
So this is simplified, we stop.
Yeah, you could stop the third or the fourth. I'd be okay with either of those. As long as you recognize some of the things to simplify, you're good.
What would the AP grader be fine?
Honestly, if it says just simplify, it's probably going to be more of a multiple choice question and you have to recognize which one's going to be correct. Good. Flip. So I did say that we would be looking at multiple compositions. This is 3, but if we can extend this rule to 3, we can extend it to 4, to 5, to 6. Anyone want to give it a go? You want to take a guess as to how you would write up the chain rule for this? F prime of G of H of X.
G prime H of X.
Yep, times G prime H of X
H prime R.
times H prime of X. Yep. So you basically just work your way from the outside all the way to the inside. I would also like you guys to go ahead and try to write up Leibniz notation for that, which you can look at the front of your notes to see how we wrote that. I'll give you a minute. Anyone want to take a guess as to what the Leibniz notation would look like? Nolan?
Is it df over dg
Take the derivative of the outside function f with respect to g.
and times g with respect to h,
Yep, derivative of g with respect to h, since that's the function inside of it.
and then times the derivative of h with respect to x.
Yep, take the derivative of h, and technically x is the function inside of it. So every function that we have would be what you're taking the derivative with respect to. All right. One last thing before we actually, bless you, get to take a small little break. I want to rewrite this using powers. Can anyone help me with that? There are 3 functions here, an outside, an inner, and then a very inside, or however you want to label it. If you want to do FGH instead, that would work. Label those, find the derivatives of those, and then we can actually put it all together. Can anyone tell me F or the outermost function? The cube root. Okay, the next inside function. So what's immediately getting plugged into that? One plus what? Perfect. 1 plus parenthesis to the what half. And then what's getting plugged into that parenthesis? X squared plus 4. Perfect. Derivative of the outside is? Yep, 1/3 parentheses to the negative 2/3. Derivative of the inner function, I guess I'll call it, or g. What's the derivative of 1? So I'm not going to bother with that, right? What's the derivative of the second term?
1/2.
Yep, 1/2 parentheses to the negative 1/2. And then the innermost function, what's that derivative? Yeah, it's 2x. How many of you still need time to write up your derivative? All right, we'll give you about, say, 45 seconds. And by the way, when you guys rewrote up that function, you didn't take the derivative yet, so you should still have that operator ddx in front of it. But once you've taken the derivative, you're not going to write the ddx anymore. Okay, anyone want to help me write the derivative up? Unsimplified, just like straight shooting, this is what you wrote. Okay, so I'm gonna take what we have off to the side and write this out, but you guys are gonna tell me what goes in the parentheses then. So first I'll write the derivative of the outermost function. 1/3 parentheses to the negative 1/3 power. What went inside of that outside function?
One plus x plus
Perfect. So basically G of H. All right, so we have the derivative of the outside times the derivative of the inner function. So 1/2 parentheses to the negative 1/2 power. What went inside of that? X squared plus 4. All right, and then times the derivative of the inside or the innermost function. Yeah, just 2x. Did anyone simplify that nicely? I mean, I'm not looking for too much simplifying, but there's some obvious stuff that you can simplify here. You see everything outside the parentheses. We have a 1/3, a 1/2, and then a 2x. At least multiply those together. And I'll write those out front. So what is that? 1/2 times 1, or 1/3 times 1/2 times 2x. 1/3 x. Now you don't need to write the x at the beginning with the 1/3, but it's a single variable with a whole bunch of parentheses being multiplied by it. You may as well write it at the beginning. And that's as far as I would need you guys to simplify. I wouldn't need you to deal with the negative powers. I wouldn't need you to put that back in root form. This would be good to leave it right here. I think the only time I would need you to do either of those things is if I had you doing anything with the derivative, like graphing it by hand without the calculator. If I had you solving for zeros or finding the domain or the range, maybe I'd have you do more with it. But for now, you're just finding the derivative. We're working on the basics. This is all you would need to do. You're talking about this x right here?
Yes.
I put that at the beginning. Yeah. If you left it at the end, that's fine. I just decided to put it at the beginning since I had 1/3 times 1/2 times 2x. And that was like a single x, whereas